So let us continue to find the moment of inertia of some simple cases. Last time I defined the moment of inertia. What is moment of inertia? The mass into perpendicular distance square from the given axis. So in moment of inertia, axis plays a very important role because it becomes different for different axes, and in rotational motion, moment of inertia plays a very important role. You can't do the mechanics of the universe without knowing the moment of inertia. So let us do the next case. That is today's lecture. I will consider some simple cases, very simple cases of 1 dimension, 2 dimension and 3 dimension. So the most simple case you can consider is the case of a uniform rod. This is the case of 1 dimension. We have a uniform rod whose length is 2a and whose mass is m. This is given to you. We want to find its moment of inertia about an axis OK. What is this axis? This is an axis passing through the center of gravity of the rod and perpendicular to it. So it will become, the moment of inertia is mass into perpendicular distance square. So mass of this small portion, what it will be? Delta x is the width multiplied by the density. That will be the mass of this very small particle which I have taken. Okay. So its moment of inertia will be that mass multiplied with perpendicular distance square. So what is the perpendicular distance here? It is x square. So it becomes 2 times rho a cube divided by 3. So it will be ma square by 3. Why it is ma square by 3? Because mass of the rod you can calculate. It varies from minus a to plus a, rho times delta x. Now when you integrate, the integral is going to be very, very simple, only x. So it becomes 2a times rho. So that gives you the value of rho. Rho becomes capital M divided by 2a. So what you have to do? In the above equation, you have to substitute the value of rho as m divided by 2a. So we have finished the first case, that is, we have found the moment of inertia of a simple uniform rod about an axis passing through its center and perpendicular to it, and it is coming as capital M a square divided by 3. I hope this will be clear to all of you. Now the next case. What is the next case? We want to find out the moment of inertia of the same rod about an axis AL. This axis is perpendicular to the rod and passing through one end of the rod. Okay. So here also you are going to do the same thing, but the only difference you will get, now you will take your x-axis as AB. You will measure the distance from A. That distance is x, and you will consider a small mass particle delta x. So the delta x will vary from 0 to 2a. in order to get the moment of inertia of the whole rod. So actually what we do, we take a small particle, we calculate its moment of inertia, and then to calculate the moment of inertia of the whole body, we integrate the result within the limits. Okay, so here delta x is varying from a to b, that is from 0 to 2a. So that is why you will get the moment of inertia about this line AL as written integral 0 to 2a rho delta x and then x square. Now again the integral is very simple. You will be getting x cube by 3 and x is nothing but 2a whole cube. So you will get the result 4 by 3 ma square. So you can see the difference. Body is same, mass is same, length is same, but if the axis is different, moment of inertia is also different. Okay, now let me take the next case, that is in 2D, to find the moment of inertia of a rectangular plate whose mass is given as capital M, whose length is given as 2a and breadth is given as 2b. The same process we will apply. First of all, we will take the small mass in 2 dimension, and after that we will be taking the next case of 3 dimension. So the second case which I am taking is to find the moment of inertia of a rectangular plate of mass m, length 2a, breadth 2b. Now again the first case about OX. So this is the rectangular plate and this is from the center of gravity. You are drawing the axes. Okay, so in this case we have to find the moment of inertia of this rectangular plate ABCD. Now because it is placed, it is a plate, so you will consider an elementary area of length and breadth delta x and delta y at a point P, you can call. What is P? Let us consider a small mass rho delta x delta y, where it is present at P, and the coordinates for P, they are x and y. Okay, now very simple. Again we are going to do the same thing, but here you will get double integral, isn't it? Because x is varying, y is also varying. This length is given as 2a, this length is given as 2b. Okay, so the moment of inertia, what it will be? Double integral about OX. We are considering about this line. So we have to measure the distance from this line. What is that? It will be y. So moment of inertia will be rho delta x delta y, and then y square, and this is the integral for x and y. X varies from minus a to a, y varies from minus b to b. I think it is clear, and you are familiar with this kind of integrals. It is no more a question of mechanics, it is a question of multivariable calculus, which you did in the last time. But of course I am going to solve it in order to recall. Okay, and the mass. Now when you solve, what will happen? You will get for x 2a let me write like this, minus a to plus a, 2 बाद में आ जाता है, चलिए. This is rho. If you integrate for x, it will be like this. If you integrate for y, it will be y cube divided by 3, and the limits for this will be minus b to plus b. That's all. So here you will get 2a rho, and here you will get, what you will get? B cube divided by 3 plus b cube divided by 3. So it will be 2b cube divided by 3. Now, the next thing, as you can recall in the last case, what we did? We found the mass. We found the value of this rho in terms of capital M. So what it will be? Here it will be rho delta x, mass will be rho delta x delta y within the limits minus a to a, minus b to b. So it will be rho x within the limits minus a to a, then y within the limits minus b to b. So it will be 2a, it will be 2b, so altogether it will be 4a, b and rho. So what does it mean? It means rho is m divided by 4ab. M divided by 4ab. So what next you have to do? You have just to substitute this value of density in this equation. So let us do it. So the result we got will be moment of inertia about OX. It will be 4a b cube by 3 into rho, that is m divided by 4ab. So it is 1/3 of mb square. That is the result. That is the moment of inertia of a rectangular plate whose length is 2a, whose breadth is 2b, about an axis which is passing through OX. Now the next case, about OY, you know, it will be similarly moment of inertia about OY. It will come out as 1 by 3 ma square. In that case, what will happen? You will consider the same mass particle, but you have to consider the distance from this axis. So this distance from this axis is x. So it will be x square, mass into this perpendicular distance is square. And then you will do the same integral, you will get the result as 1 by 3 ma square. Now let us find out the moment of inertia of this about an axis. This is A, you can say, this is B. Now C, to find moment of inertia about OK. Now what is this OK? An axis perpendicular to the plate and passing through its CG. So what will happen now? The mass is going to be the same as you have the same lamina. So density will be m by 4ab. Let me write it here. And let us calculate this result. Of course, if you have followed the procedure, you can do it very easily. It is equivalent to double integral minus a to a minus b to b. Okay, then rho delta x delta y, this is for mass, and then perpendicular distance square. Now see, what is the perpendicular distance square? This is x square plus y square, isn't it? This is under root of x square plus y square, the distance between 0, 0 and xy. So we need perpendicular distance square. So it will be like this. Okay. Now again it became a problem of multivariable calculus. So you will get the result. You will get the result as m by 3 a square plus d square. If you have any doubt anywhere, you can comment in the comment section. Okay. I hope you can find the moment of inertia of a rectangular plate which is in 2 dimension. You have taken an elementary portion of it it is delta x delta y, and then you found its moment of inertia about x-axis by multiplying it with mass into perpendicular distances square, about y-axis mass into perpendicular distances square, and then about an axis OK, which is perpendicular to the plane of the plate, perpendicular to the plane of the blackboard, which we cannot draw, so that is why I have drawn the dotted line. And you know that will be again rho delta x delta y, that is for mass, and then perpendicular distance is square, perpendicular distance between the two, one is 0 0, this is nothing but 0 0, and another is xy, p is xy. So perpendicular distance between 0 0 and xy, it will be under root of x square plus y square. So perpendicular distance square will be like this. Okay. Now the last case which I want to do today, that is the case of a rectangular parallelepiped. That is the case of 3D. So let us do it. Let us first draw the figure. Now to draw the figure, all of you know we have to consider a rectangular parallelepiped whose mass is capital M and whose sides are 2A, 2B and 2C. So let us do this case. Moment of inertia of a rectangular parallelepiped of mass M and sides 2A, 2B, 2C. First, about OX. Okay, so this is our question. Now, we have to draw a rectangular parallelepiped. So this is our rectangular parallelepiped, sides are 2A, 2B and 2C. This is your x-axis. Draw the axis like this. This is your x-axis. This is your y-axis, this is your z-axis. So that is the figure. Okay. Now, the same procedure we will apply. We will consider our elementary mass whose length is delta x, breadth is delta y, height is delta z. So the mass is going to be, M will be rho delta x, delta y, delta z with the triple integral. Now what are these triple integrals? Minus a to a, minus b to b, minus c to c. So they are going, this x varies from minus a to a. So you will get 2a, y varies from minus b to b, you will get 2b. Z varies from minus c to c, so you will get 2c. So what will happen? 2, 4, 8. 8 A, B, C, rho. I have done it orally, but you can do it. Okay. Now, this implies that the density is m divided by 8 A, B, C. Okay. Now, moment of inertia. Moment of inertia will be again triple integral. Mass is same, rho delta x, delta y, delta z. Now, its perpendicular distance is square from x-axis. You know what it will be? Very simple. Under root of y square plus z square. So it will be y square plus z square. Under root will be removed because we know the moment of inertia is mass into perpendicular distance square. I hope this is clear. Now again the integral is from minus a to a, minus b to b, minus c to c. Okay, so you will get the result. What it will be? Calculate this and find out the result for rectangular parallelepiped. Okay, and tell me in the comment section the result. So this I can say this is your homework, and next time I will tell you the value, I will tell you the result. Now one more thing. This is the moment of inertia about OX. What will happen if it is required to find the moment of inertia about OY? Here you will get no y, you will get x square plus z square. If it is required to find the moment of inertia about OZ, then it will be this much, and no z here, you will be getting x square plus y square. So that's all for today. I will give you the results in the next lecture so that you can tally them. Okay? After integrating this, what next you have to do? You have to substitute the value of rho. Rho can be substituted right now as well because it is independent of x, y, z. So it will be simply m divided by 8abc, and then this triple integral, then you have y square plus z square, and then dx, dy, dz, and minus a to a, minus b to b, minus c to c. So guys, that's all for today. We'll meet on the next turn, and then we will find out the moment of inertia of some more simple cases that will include some circular, some different figures in 1D, 2D and 3D. Okay, thank you very much.